whenever resistance is increased, we will get a bend. We will get a bend here. Now, after this, we start increasing VDS more than VGS minus VT. More than VGS minus VT. Then at certain point we get a saturation. That means the current will be, this RDS will be going on increasing, VDS is increased, and at certain point the current becomes constant. So at certain point the current becomes constant. That point is called saturation point. Okay, we obtain the current relation for saturation point as by making VDS equal, we obtain the saturation point at VDS equal to VGS minus VT. Just to substitute here, we get ID equal to mu n C of W by 2L into VGS minus VT whole square. Okay, this is the equation for in saturation. This is the equation in linear region. Okay. Right. Now here, this is mu n is given, will be given. Cox is oxide capacitance is a constant. W by L is a constant. It's an aspect ratio. VGS they will give, VT will be given. Now we finding ID will be very easy. Now let us consider a small example to check whether the transistor or MOSFET is in which region. Okay. Now we have got these two equations. I'm erasing this. This is equation A. This is equation B. Okay. Now consider they have given these parameters. VGS equal to 900 millivolt. VT equal to 400 millivolt. First case. VDS equal to 250 millivolt. Second case. VDS equal to 600 millivolt. Now they are asking to find whether in which region MOSFET is operating. In which region MOSFET is operating for these two voltages. Okay. First step we need to calculate is whether, step 1, whether VGS is greater than or equal to VT or not. Because channel will be formed only when VGS is greater than VT. Okay. If not, it will be in the cutoff region. Now if you see VGS, it is 900 millivolt and VT 400 millivolt. So this step is satisfying. Next, step 2. If VGS is greater than or equal to VT, but VDS is less than or equal to VGS minus VT, then now we'll see. Consider the first case. First case, VDS equal to 250 millivolt. 250 millivolt. VDS is 250 millivolt. Okay, less than or equal to VGS minus VT. 900 minus 400, that is 500 millivolt. So what we got is 250 millivolt minus is less than or equal to 500. This is correct. Okay. Now you can check for this condition. If this is true, then this condition won't be true. This condition won't be true. So whenever this condition fails and this condition is successful, so the MOSFET is lying in the linear region. Now you can find the ID by substituting in these equations. This constant will be given as some 130 volt per meter square hour. Okay, substitute this specification of VGS, VT and voltages in this, we get the ID. Now consider second case for 600 millivolt. Now in the second case, VDS is given as 600 millivolt. 600 millivolt less than or equal to 500 millivolt is not possible. So it should not be in the linear region. And see that VGS is greater than VT. VGS is greater than VT. That means we are in the cutoff region. And 600 milli and VDS is less than or equal. VDS is not less than or equal to VGS minus VT. So it is not in the linear region. So if not in the cutoff, not in the linear, it will be in the saturation region. So we get VDS is greater than or equal to VGS minus VT. This will be 600 greater than or equal to 500. This is correct. Okay. This is how we check for the transistor to be which region in operating in which region. So the conditions are to be in cutoff for a transistor MOSFET to be cutoff, VGS should be less than VT. VT is the threshold voltage. Okay. So for the MOSFET to be in linear region, VGS should be greater than VT, and one more condition, VDS should be less than or equal to VGS minus VT. For the MOSFET to be in the saturation region, VGS should be greater than or equal to VT. VDS should be greater than or equal to VGS minus VT. Okay. Due to high increase in the drain to source voltage, what happens is initially the channel is this manner. Okay. Slowly with the increase of the drain to source voltage, the channel will pinch off like this. This is called pinch off effect. Okay. And I already mentioned, as our voltage is increasing, the channel will be decreased, so that electrons flowing will be decreased. The electrons flowing will be decreased, and this decreases the conductivity, so that this increases the resistivity, and thereby resistance increases. This is all interlinked. Okay. So that's all for this video. Thank you.